Hello, Niranjan. Good morning.
Good morning, Dr. Hadish.
Hello. Is that too much? That's a homework 7 that was due today. Posted homework 8. Yeah. Hopefully, we'll be able to finish complex analysis this week, and then we will start. Maybe we can say quantum spaces or just partial differential equations. That's what broadly we can call it, or Green's functions, right? That's the way I like it. So that's what we will see. Okay. Any comments you have? Anything I should address here? Oh. Okay. We are doing complex analysis, mostly at this point integrals. So let's contour integrals. And the idea is basically based on analytic function. So we have analytic function. And what is an analytic function? If you have z, which is equal to x plus iy, and if you have a function f of z that's equal to u, which is a function of x comma y, v is a function of x comma y. Mostly the simple idea will be to satisfy Cauchy-Riemann conditions. Conditions, and often it is written in terms of u and v, but it is convenient to also think of it as the partial derivative with respect to z star is equal to 0. First, you want to write this function as a function of z and z star, and you just have to show that there is no dependence on z star. The function is purely dependent on z, not on z star. So immediately, if you see a z star dependence, then it's not analytic. These are necessary conditions, but not sufficient. You might always miss some points. So even though this is very, in the first elementary level, very useful, but what is more useful is where it is not analytic. So where are they usually not analytic? That's a harder question to address. When you're saying non-analyticity, it is a very broad idea, and we often do not know what causes that, or it's not easy to characterize this. We will here concentrate only on two things. One is whenever there is a simple pole. This came up last time, and that will be whenever the function has a structure of the form 1 over z minus a. If you can isolate it in some region, there is some z minus a structure in there, this will be considered a simple pole. If it is z square, if it is z minus a the whole square, that can be converted into a simple pole. So think of partial fractions, or even if it is second order, you can use differentiation by parts and convert it into a simple pole. But most of the time we are talking about this based on, or we will find ways to use this to the biggest extent. That's going to be the primary idea, and that's what contour integrals will depend on. But the second point will be a branch cut. Branch cut is basically a discontinuity. So a discontinuity. And usually it is along a line, as we will point out. This is not necessarily an infinite structure. Think of, for example, let me not do this here. This can be a quiz. So you have a function. So this is the z plane, and let us say the function is 1 over square root of v. And evaluate the value of the function at point A. So let me call this point z1, and that's point z2. I'm approaching the positive real line from the 2 points along that dashed line, and my question is find out what is f of z1 minus f of z2. I should also point out here there's a choice here, right? So let's say z is equal to r times e raised to I theta, where theta is less than 2 pi and greater than or equal to 0. So, and that's your angle theta. So you evaluate this function when you're coming from the top, evaluate this function coming from the bottom, and the claim is that this is not continuous. So evaluate the discontinuity in there. So these kind of functions we will, in fact, it won't be always a disadvantage. We kind of exploit it. It's exactly like this. In the first level, oh, this is not analytic, it's not very useful, but then you exploit that feature, that whenever it is of that particular form, it has some feature, and we try to evaluate that integral based on that. So based on this, we had what is called Cauchy's theorem. And Cauchy's theorem is mostly about the simple pole, and we said that we have 1 over 2 pi I. If we go along a contour C around v minus a, so this is the simple pole that has been isolated, and whatever is in the numerator is analytic. This is analytic. 1 over z minus a is most of the places analytic, but it's not analytic at z equal to a. It is infinity there. And here we said that this is equal to f of a if a is inside the contour C. So C is a closed contour. This circle means that it forms a closed loop there. It's a closed loop contour, and if A is inside the contour C, then you say the value of the integral is f of A, and it is equal to 0 otherwise. That means if A is outside that loop, then it is equal to 0. This is often called the residue. So this is equal to residue. I often say this is the residue theorem and so on, but that's mostly Okay. So let's do an example. So I feel a clear-cut example which appears in physics often helps to illustrate this feature usually. And a very fundamental expectation in physics is that whatever we measure in the lab or in a whatever theory we propose should be causal, right? What does causality mean? Have you heard of causality? Can you think of any phenomena that is not causal? Maybe first let's begin with what is a causal. How would you define causality?
The maximum speed is C.
Causally?
Yeah, maximum speed.
Maximum must be.
Speed of light. So we can go.
Yeah, that is, or you're saying special relativity uses the feature of causality. But even otherwise, in general, we expect that whatever happens, there must be a cause before, right? Or a very dramatic thing would be I shoot, let's say Aryan. I shoot Aryan and Aryan dies before I shoot him, right? That's not causality. He has to die after I shoot him, right? Otherwise, the cause happens before the effect. I cannot do something whose cause happens later on in my life. So that's a very simple statement. But now to implement that, that involves a lot of that's a lot of constraint you have put in. Just the fact that everything that causes an effect should be before the cause, that's a huge constraint, I'm saying. And we will see that that will involve ideas like contour integral. So that's one of the very good examples that we have. So let's do this in physics, right? So these broadly can be called response functions. Response in the sense of I do something and something happens. Correct? That's what I meant by response. And this comes up when you're doing electrodynamics. So almost all of you, or two of you have already completed, others are doing electrodynamics. You go right away after this class. And there you talk about something called a dielectric constant. What is a dielectric constant? What comes to your mind when you say dielectric constant? So maybe I can say, so there's a material and there are dipoles, right? Negative, positive, positive, negative. So this is positive, negative, right? Negative, positive. And you put in an electric field in this, and they orient themselves, right? That's a response. I provide an electric field, they respond by rotating, right? I put in, so there is some weather phenomena and we all react to that. So this is an external electric field and they all align themselves with the electric field. That's polarization. Okay, so we often say for polarization at position R at time t. Notice that's where the causality will come in. Causality has to do with time, right? So the polarization at some position inside a material at time t is decided by what you externally put in. That's the electric field. That's also a time dependent quantity and a position dependent quantity. This is decided by the material, and the material property usually involved is time. This can be a dyadic, but let's keep it simple. Let's say it is an isotropic material. It doesn't matter in what direction the electric field is. Let me just put it very well. This is a dyadic, and this can now depend on position and time again, right? And this is called the, what is this called? And susceptibility, and that is given in terms of the dielectric constant. So chi is equal to epsilon over epsilon naught minus 1. These are all R and T dependent. This is a vector, that's a dyadic, so I have a dot product here. But now, what is there inside in here? So you first say that the polarization at position R, can it depend on the electric field somewhere else? For example, whatever I am going to do here, if I'm a charge, how do I react to the electric field, let's say in New York, or is it the electric field at this position that decides it? And in principle, it could be anywhere, but most of the time we say that it is the electric field at my position that decides my effect. So that's a positional dependence. I'm not coming in time yet. And that's called local interactions. We often say that interactions are local. It could be that there is something else at another point coming in. That's a more complicated interaction. For us, we are interested in causality. Let's not go into the position. So let's just say that this is R. It could be R comma R prime. That's what I mean. So this could have been R prime, and then I can integrate over dq R prime. So I can say that the interaction or whatever happens to this dipole at this point is having a contribution from everywhere in the world. That's possibility. But we say that now let's keep it simple. So this is this integration is not there. This R prime is not there, and this is equal to just R. That's called local interactions. We are saying all the interactions are local, and most of the time when we build models, we are talking about local interactions. But that leaves us with the time, right? So I'm saying that from here to here, I use local interactions, and then I'm still having time in it. This is time, prime, so that is chi of R, and I still have P prime dotted with, let me make it isotropic, so that the dyadic nature is not there. Again, simplicity alone. This is E of R comma P prime now. And I again integrate over P prime, and this is what I'm interested in talking about here. What times does it matter? So the simple fact that it is causal means that this T, this is what is today, the present, is affected by the past, not from the future. Future cannot affect us, but past affects us. That's the idea of causality. If future can affect us, that's a proposition you can have. You can have a different theory, and if it explains whatever we see, that is good enough. But we are saying it is future does not affect us, and that means that it is only the past. So P prime cannot go in the future, so you have to put a limit on this. So that's P. That's causality. So this feature here is causality, or the requirement that P has to be less than, or P prime has to be less than T. So because T prime is a source, right? So let me put this again. So this minus infinity to T, T prime phi of R prime, and then this also requires, now there is one more feature that goes in here, and that is that it should be translationally symmetric, right? Whatever is the response yesterday, you do an experiment with a sample yesterday, and if you do it tomorrow, it should not matter. The result should not depend on when you're doing it, and it could be as early as Big Bang, like it could be in another galaxy in a very, very, very millions of years back. You say that your equations of motion are still the same. It is the same Maxwell's equation that go on. It may not be, but if not, then you have to change your equation. So this is translational symmetric. Again, just to motivate these ideas, we won't dwell into it too much. And that's electric field. So this is where the idea of causality comes in, that you put just a drastic cutoff there, that no, there's nothing else that is possible beyond that. How would you mathematically do this? This is whenever you put this, if you're doing any, there is beyond quantum mechanics, you do quantum field theory. And in those subjects, whenever you have a limit on the integral, it's not convenient, mathematically convenient. It is not easy to work with integrals that have a limit. So you want to take away the limit and put it into the material property. So instead of talking about a mathematical structure, you say that, oh, the property of the materials should decide that. I mean, materials should know that you should not behave causally, if you want. It should not violate causality. So you say that, okay, there's a new property now, F instead of chi, which involves this piece in there, but that is done very straightforward. Okay. And that is where, and that is what we want to explore. That function is what we want to explore. Is equal to a step function, t minus t prime times chi. Okay. Where step function is equal to the t minus t prime is equal to 1 if t is greater than t prime, and is equal to 0 if t is less than t prime. Like very simple function. Now, this is the susceptibility. Susceptibility is related to dielectric constant, and dielectric constant is related to the refractive index. That's not a very common thing, at least in elementary physics, we don't stress on this. The refractive index in optics that we study is nothing but the dielectric function that you have, which is a square root of epsilon. So the refractive index n that you see is nothing but square root of epsilon. Okay. This is refractive index, for example, 1.5 for glass. The speed of light is decided by this, which means that if you're the best places where you can experimentally measure these things is in optics, and optics is a very color dependent quantity. Like most of the optics experiments are done using frequency, right? You use how does the red light behave? The refractive index is a very color dependent quantity. You usually don't talk about refractive index as a function of time. Like here we have all time dependent quantities, right? Where is the color in here? Any comments on that? Where is the color in there? Time? Huh? In the chi. Better answer. Yeah, inside of chi. Epsilon is chi is this. So epsilon is in here. So square root of epsilon means it will be chi plus 1. But that is all time dependent. Where is the color?
It's related to time.
And how is it? Yeah, very good. It's frequency, right? Frequency is what color is. And frequency is Fourier transform. Like to some extent, all of us are familiar with some idea of Fourier transform. We'll do this in more detail in a week or two. We'll come back and study Fourier transform. But the basic feature is that a Fourier transform of time is frequency. What is the Fourier transform of position?
Momentum.
Yeah, wave. Yeah, actually, that's better. Yeah, momentum is wave number, maybe. Okay. Like mass you're multiplying. Yeah, good. Momentum, or you will say wave number, or 1 over wavelength. Like wavelength is the periodicity that you can usually visualize. That's what I would say. But frequency is the correct. Momentum is the better answer. I would say. So usually you would say Fourier, because you want to do optics, you do a Fourier transform of this, which would mean that There are three pieces in there. Let's take these two pieces. So you would say you would like to talk about frequency dependence of the step function and phi optical properties which are frequency dependent. Instead of talking about time dependent quantities, you can talk about frequency dependent quantities. So we are suddenly talking about Fourier transform, and that's where this contour integral comes in. So this is all the motivation for that. So we want to do the simplest function, probably the simplest function, but it's not simple. We want to find a Fourier transform of this step function. That one might think that it is very simple because it's 0 and 1, right? There is only one feature in that step function. What is the Fourier transform of that? What is the Fourier transform of step function? You know the Fourier transform of any function. What's the Fourier transform of sine function? We'll come back to this Fourier transform a little better, but for us at this point, it's just an integral. So if you have a function f of t, maybe not use f, right? Because we are using an analytic function. Let's say f. Hopefully it's not confusing. You can write this in terms of exponentials. You say this is d omega over 2 pi and e raised to, if this 2 pi is there, or whether it is square root of 2 pi or 2 pi is a choice. And this is minus I omega t, and this will be the Fourier transform. So this function, that it is frequency dependent, is called the Fourier transform of the actual function. You can go from one to the other using these integrals and go by this. That's the basic idea, that instead of working in time, you work with frequency. And once you have done your job in the frequency space, you have to come back to the time space. So you do the inverse Fourier transform to do that. And clearly it involves integrals. So you should be able to do an integral. And if you have this function to be a sine function, then these integrals are easy. Well, that's one of the easiest integrals you can do. Sine function can be written in terms of exponentials, and exponential integrals are relatively easy, but these are oscillatory exponentials, and it turns out these are delta functions. So sine function has this Fourier transform that it is a delta function, and this appears in quantum mechanics also very much, that if you have time dependence, so let us say there is a time dependence of this kind, right? So this means that time is constrained, right? So the most of whatever things are happening is confined to a certain region. Let's call it tau. If you try to do this in the frequency space, this will spread out. This now is, let us say, frequency is omega naught, and it is in such a way that omega naught times tau is approximately 1. If you have a function that is confined in time, it will spread out in frequency. If a function is constrained in frequency, it will be spread out in time. Sine function is oscillatory and it is spread out in time, right? So it is not localized in time, but if you go to frequency, it has only one frequency allowed with it. How many times is it oscillating? That's only one. So frequency times time has this very intuitive feature that one is the opposite of the other. And in quantum mechanics, this shows up as uncertainty principle. Like if you confine your position, momentum is not confined. If you confine your energy, time is not confined, and so on. So that's because of this feature. we are interested in the step function, right? So we would like to know. So we are interested, this is our example. We would like to know what is the integral dependence or Fourier transform of a step function. And that's equal to minus infinity to plus infinity, omega over 2 pi. And let's call it. Often, very soon, like when we do Fourier transform, I'll drop this tilde on it, and it's understood that the frequency dependence will tell us that it is a Fourier transform. I'm interested in finding this step function is given to me. So it seems like I can just do this, right? I just do the inverse of that. dt and step function. And the step function is Heaviside step function, okay? So this is t time. That's 1, that's 0, and it is 0 everywhere onto the left, and it is 1 to the right, right? That's our understanding of step function as I defined it. Here, if I integrate that, I should get the Fourier transform of that. So one would expect that it should be very straightforward. And let's do that integral. So that's equal to, so this is from minus infinity to, so when I go from minus infinity to 0, the step function is 0. So it doesn't contribute, it is 0. So notice I put a 0 there. And after that point, it is 1. Right? And that's an exponential integral. What is the integral of this? What is this equal to? Sir?
E to the power I omega t divided by I.
Yeah, so e raised to I omega t divided by I omega. And you have to evaluate, right? At t equal to 0 and t equal to plus infinity. And what is that equal to? No? Yeah, good. It's not well defined, right? I thought that's what you said, right? Exponential, these are oscillatory. At t equal to infinity, I don't know whether it goes to 0 or 1. It could be anything between minus and 1 and 1. It's never clear what exactly it does at infinity. So this is not well defined. So a very simple feature, notice we were talking about response functions. And if you want to find response functions, we are talking about causality. And the simplest way you can put in causality is to put in a limit on that. And the moment you put in a limit, you seem to be having trouble with understanding how to do this integral. So how you manage this is that, okay, this seems to be not well defined. So we want to make it defined, but you have to change the physics somehow. And here is how you would change it. So you are saying that I'm going to change this. So this is not what we will do. This is not what we will do here either. So we want to change the material properties in such a way that we would like to do minus infinity to plus infinity et and e raised to I omega. And now change this. So let's say plus I delta times t. What I've done there is that, right, so notice what is going on in here. And I have to take a limit, right? Limit delta tends to 0 from the positive side. Right? Delta is greater than 0, and you come from the positive side. So basically, you have put in this is dt e raised to I omega t times e raised to minus delta times t. So what kind of model is this? What we are saying is that step function was equal to 1, 0, right? This is t greater than 0, t less than 0. They're saying that, oh, that seems to be too expensive on the analytic behavior of the function, or it is divergent, is leading to divergence. So we are going to say that, okay, we'll do it slightly better. So I'm going to say step function is going to be exponential of minus delta t instead of 1. This is 0, and this is t greater than 0, and this is t less than. Okay. If you recall, exponential feature has this piece in there. And you will ask at what point does, so there is to be a scale somewhere, right? This is exponential of delta t, that's t. There has to be some scale here. When this becomes 0.63, what is this called? A special name for it? An exponential function when it falls to 63% of the value. Like I think it tries to fall further down, I think, somewhere here. Yeah, half-life, yeah, or time constant, very good. So you say this is time constant, very good. And that is got by 1 minus 1 over e, right? The exponential e is 2.7. And that decides the time constant. And what we are saying here is that delta here, 1 over delta, is the time constant. So when we say delta is really small, we are saying that the time constant is very large. So that's the model we are putting. If you say it is 1 and 0, it is really infinite time constant, but we don't want to make it infinite. We are saying it's a very large time constant. Okay, that's the interpretation of this delta. So if you think of responses, we are saying that we want all the past to affect our present, but not all the way to infinity. So we are putting a cutoff somewhere at the end. Very, very far in the past is not affecting it. That's the delta. Okay, most of the past is accommodated, but we give preference to what is in the closest. So what happened yesterday affects me more than what happened a million years back. That's the new model, and that basically changes this integral in this manner. And let's but all this is modeling still. So we are saying theta of t now is exponential delta t and 0, t greater than 0, t less than 0, and the Fourier transform of this apparently is straightforward. Delta tends to 0 and minus infinity plus infinity dt and exponential I omega t times so we have exponential minus delta t if t is greater than 0, 0 if t is less than 0. If t is less than 0, it is 0. So I have limit delta tends to 0, 0 to infinity dt exponential of I omega plus I delta times t. Right? That's a way of writing it. I put -1 is I square, and I have omega plus I delta. Do the same integral that you guys were suggesting. Now I have this delta that will help me take the limit, and you said this is nothing but I omega. Let me find this better. So e raised to I omega t, e raised to minus delta t divided by I times omega plus I delta. And I will evaluate this at t equal to infinity and at t equal to 0. Now, if you notice, at t equal to infinity, this is well defined. This is oscillatory, but this is decay. And for small delta, that no, at t equal to infinity, as far as delta exists, at t equal to infinity, it will kill it to 0. So the top one is 0. The bottom one is minus 1 over I. The denominator stays the same, and at t equal to 0, this is simply 1. So now we have a Fourier transform of a step function. Notice how hard it is to visualize some function which was so straightforward in time space. In frequency space has this feature, right? Whenever you see a 1 over omega, 1 over the frequency next time, you should realize that in the real time space, that corresponds to, that is what is making it causal. So it is important that you have that omega, 1 over omega p's, and it's very common if you were to see some property of refractive indices of something, so you will always see this 1 over omega feature in there. And the delta is also important in the sense it is there to convert. But we said we would like to, this is an example of contour integral. We haven't really used any contour integrals here. It's the opposite that is important. Now that we have the frequency or the Fourier transform in the frequency space, we should check that if you really do this integral to the inverse, you should be able to get the step function. And for that, we will use contour integral. So let's do the following exercise. Half an hour of motivation, but I think it's crucial. So let's say have minus 1 over I, 1 over omega plus I delta. That's a simple function you have, and I'm interested in calculating the following integral. We know that that's a step function, but we want to test that. We want to check that. So this is equal minus infinity to plus infinity to omega over 2 pi exponential minus I omega t, and step function. Step function, yeah, and that is the same as I can bring out the minus, so this is minus 1 over 2 pi I minus infinity plus infinity omega exponential minus I omega t divided by omega plus I delta. I wrote it in such a way that this is that Cauchy's theorem kind of comes in. But if you notice, Cauchy's theorem is 1 over 2 pi I z f of z divided by z minus a is equal to f of a or 0, right? It is inside of the contour. So what is this equal to? Be very careful, I'm tricking you. What is this equal to? I'm tricking you, so be careful. And how do we use this in here? What is that equal to? What is the residue? No. Notice omega here is real, right? We are on a real line. This is a complex variable, right? You're not there yet. It looks like that, but we cannot do complex integral that way. We need a complex plane. We first need to go there. Then we need to define a contour. All this is remaining, right? This is not a complex integral to begin with. We are doing it on a real line. Omega is not even a complex variable, right? But so that's where the point of. But this is on a real line. So let's go to the complex line. So let's not do theta function at all, like the step function at all. We go to a new function, so that's g. I'm now upgrading myself, but I can do whatever I want. So I'm building a function, and this is the most hardest part in complex analysis. That which function do you consider that will help me do this integral? In these matters, it is easy because I'm going to almost write the same thing. So I'll do 2 pi I. Let's keep it pretty much the same. But now I'm going to switch omega to z. I've gone into the z plane. This is e raised to minus zt. And this is z plus I delta. The only thing I changed is omega to z. But that might work in this case, but in general, that may not work. We will do another example in which it will be a cosine function, and you don't even do this. You have to come up with an entirely different trick. Right? So that particular cleverness is what is mostly the challenging part of it. But then this is all to exploit that integral. So how do we, what was the motivation in doing this? Notice now you don't say minus infinity to plus infinity. Now you have to define a contour. Right? A complex integral involves a contour, at least a closed contour. So let's say this is contour C. And what is the contour C? So now I'm in a complex plane. This is Z. And T, notice, is still your time. There are two variables in here, Z, T, and then there is a delta. So in delta is a limiting factor, but mostly there is two variables, Z and T. T is still real. Z is where the integral variable is what I lifted it to a complex plane. First, I should look at what I'm interested in. This is what I'm interested in, and Z becomes omega in some sense, and that is on the real line. So I'm somehow interested in this part. When I integrate on this line in this complex plane, I get this integral. Right? When I integrate on this real line of this complex plane, I am identifying that with omega. That's what this is. So I would like this to be part of my contour, but I have to make a loop if I want to use Cauchy's theorem. So I make a loop out of it. Now there are two possibilities. I can do this way or that way. Both might be important, but let's say it is this. I'm not sure about this. We'll come and investigate this. This is plus R, let us say, and this is minus R. And obviously, if I want to connect with this, R should go to infinity. That is going to be my contour. So let's say this is C1 and that's C2. So C here is C1 plus C2. And it is not even clear that is this whether should I go up or down, and you will say that some cases you will go up and some cases you will go down, and I'll come to that in a minute. Is that clear? And we also say that R has to go to infinity. Eventually you want to take this all the way to infinity, and that's how you will get this. There is a Z plus I delta. Where is that? When does this goes to 0? This goes to 0 when Z is equal to minus I delta, and that's somewhere here. That's the pole, minus I delta. Right, so that is the pole. Okay. Question, yeah.
Why did you choose the real line?
Why did I choose a real line? Because I want when Z is equal to real, so when Z is equal to omega, so on the real line, Z is equal to omega plus I times 0, right? Y is 0. So omega is my real one. So on this integral, when I define my contour, I'm going from minus R to plus R. In the limit R tends to infinity, it is minus infinity plus. So this part of the integral is what I'm interested in. Right? So I want that piece to be somewhere there, at least some trick I should be able to use to get part of that integral. Did I answer the question? Any other questions? Yeah. And that is the most important thing. In at least in the worked out examples, you do this, but then as you proceed further, whenever you're writing new stuff, like this, going from here to here is the hardest part and the most creative part. Rest, everything is mechanical. Okay. If this is the case, what is this equal to? Now I know this is, now I can use Cauchy's theorem. What is this equal to? It's equal to 0. Very good, because the hole is outside. So this is equal to 0. So that's 0, right? So we know that this is equal to 0. Okay, right? One might think that, oh, is that not that may not be useful? No, that's useful because we are saying that this is only part of it, right? So we are saying this is minus 1 over 2 pi I contour C1. Now on the contour C1, it is real. Let me write this 2 times over Z plus I delta minus 1 over 2 pi I C2 Z plus I delta is equal to 0. Right. On the real line, Z is nothing but omega. Right. On this case, Z is equal to omega plus I0. When it is omega, that's exactly theta function. So I know that this is theta function. The first piece is theta function, which is equal to, or second piece is 2 pi I. And on this semicircle, I know that I can substitute. So in this case, I substitute Z is equal to, R is fixed, right, on this semicircle. So it is R times e raised to I theta, where theta goes from 0 to 2 pi. So dz is equal to I times R e raised to I theta times d theta. So that's the integral I want. So if I do this integral, I know theta of t because it's on the, I can take it on the right side. I'm evaluating it. So notice, I'm interested in this part of the integral, complex plane, but I'm not evaluating that. The idea is to not evaluate that, instead evaluate somewhere else, which is simpler. It is like doing, I think last time I was giving the idea of potential energy conservation. If you want to calculate what is the potential energy, gravitational potential energy when you go from here to your home along a complicated path, that might be very hard because the path itself might be very hard. But instead you say that gravitational potential energy only depends on the height. Calculate the height of your house, calculate the height of your office, and the difference in the height is all that is needed. Right? That's a different path altogether. So same thing here. This might be hard, maybe hard, if it is hard. Instead, go there, and often it is easier. So you want to find a suitable contour where your integration is easy and connect it to what you are interested in. That is what contour integral is all about. One point, since you have this analyticity feature, Cauchy's theorem, use one to connect with the other. So let's try to do this integral then. So this is theta equal to 0, theta equal to pi, and this should be well defined. Only if this is doable, we can do that. So this is dz is I times r e raised to I theta and d theta. And this is equal to exponential of minus I. Z is r plus I theta. So let me write this as, r cosine theta plus I r sine theta. I'm doing that investigator feature, and divided by z is plus I L, and that's equal to 0. So basically, theta is the integral of this. Okay, so write this again. It is equal to 1 over 2 pi I. There is an r in the numerator. I can also pull an r out here. So because r is large, remember r is very large here. So this can be written as, let's see. So I, so d theta 0 to pi. And how could I do this? I times e raised to I theta. And let me write this as minus I r t cosine theta. And this is minus I plus I, so that is plus p r sine theta. And divided by exponential theta plus I delta r. And all this is in the limit r tends to infinity, that is understood. Good thing? This is now a angle dependent quantity. We are working somewhere here. So for each angle, we are asking what is the value of the function on this contour here, C2. If it is convergent, that is good. For large R, what happens? This is oscillatory. Let's investigate the quantity. What happens at large R? This is oscillatory. What is this exponential equal to for large R? So let us investigate. So use this. So we have a feature there that plus t r sine theta. What is that equal to? For large R, like on this contour C2. On C2. What is that equal to? So let's see this. For large R, if t times sine theta is greater than 0, right? Exponential of t times r sine theta is equal to, in the limit r tends to infinity, is equal to infinity, right? If this is greater than 0, exponential grows, that goes to infinity. If t times sine theta is less than 0, limit r tends to infinity of exponential of t r sine theta goes to 0. Agreed? But is sine theta really positive? Notice here angle is 0 to pi. Sine of theta is always positive from 0 to pi. So this is in fact valid. So we would like this. So this is sine of theta is greater than 0 for theta less than pi. So that's okay. So which means to say that, and we don't want to work with infinities. Infinities are not doable. That's not possible. We never deal with that. So instead, we would like this. How can I make this less? The only possibility is time t, right? T was still open for us. So we can conclude at least one thing. So for t less than 0, right, this integral is equal to 1 over 2 pi I. I take the limit r tends to 0, that immediately goes to 0. This integral is done, kind of, right? 0 to 2 pi. Theta. I take the limit r tends to infinity, so exponential goes away. So I have I e raised to I theta. This is e raised to I theta plus I delta over r. Trying to take the limit. This is minus I r p cosine theta. Whatever it is, this is what is important. This goes to 0. So that means this is equal to 0. So this is equal to 0 for t less than 0. This is okay. That's what we wanted, right? Our step function was equal to 0 for t less than 0. So that came out even without doing an integral, without But we did use Cauchy's theorem, right? That we went to the other part of the integral. But then we would like the one part of it. For t greater than 0, we would like to do this. So now look at this again. We started from here. We went till here. We are now interested in t greater than 0. What should I change in this so that I can do this integral for t greater than 0? Huh?
The contour.
Very good. Very good. That's exactly what we will do. So remember, there was an option here that we went on top, right? We have that freedom still. So for t greater than 0, let's try this. It's not very obvious right away, but that's it will turn out to be exactly what is needed. So let's do the contour. This time, instead of going this way, go the other way. And remember, Cauchy's theorem always is for counterclockwise. Okay, so we are going in the opposite direction. So we should be careful if we are using the Cauchy's residue theorem, but in this case, it's just a contour, right? So this is, let's say this is C1, and that's C3 this time. And we have a pole, minus I delta, right? Minus I delta. We again say this time G of t, right? So let's say G of t, let's call that G1t, and this is G2t. This is another function altogether because now I've changed the contour. My function is completely different. So this is G1t and this is G2t. So G2t is equal to minus 2 pi I. This is C1 plus C3 this time, dz, and e raised to minus I zt divided by z plus I guess. Again, I should stress that I asked a question just a few minutes back as to what should I change. That is the hardest part in this whole problem, as to figuring out what should you change so that you can get an answer. So that oversight is what is the hardest part in contour integral. Most of the time we work with worked out examples, so we keep repeating the same ideas. But if you're doing a new thing, that's what we need to do. What should I do something here so that somewhere else can be used? It's the idea of a conservative force. Potential energy idea, all these are connected in many ways. But now, let's do this is C1 or C3, right? Sorry, C3. Again, the same idea. The first contour is C1 is your, and what is this equal to, by? That's a closed contour. Use Cauchy's theorem. What is that equal to? It's a residue. It is not 0 now. It has a pole, right? Z plus I delta is inside the contour, so it has a pole. So it is 2 pi I is there, so it is minus of that. So it is minus of exponential minus I. Z has to be replaced with minus I delta and t, right? Minus minus. So this is presumably, I guess. So this is help me. So this is minus, right? Yeah, minus delta t. Okay. And
What did you have? The negative sign?
I think it is this negative sign. There is no negative sign here, correct? What negative sign there? Correct? Check on me. I'm doing it here. I don't remember the answer. Hopefully the other one will give you a minus sign somehow. Yeah, do we have a minus sign there? Oh, yeah, there is no minus sign. Why is there no minus sign? Because remember, Cauchy's theorem is for counterclockwise. We are doing clockwise, right? Is that clear? What I made the mistake? So we are doing clockwise. Cauchy's theorem is for counterclockwise, so this is clock. So there is minus and a minus. Too many minuses. This is because clockwise. So this becomes a constant. And in the limit delta tends to 0, that is indeed equal to 1. So I have, so C1 will be my step function again. And this time it is minus 2 pi I. And I do the same thing now. This is on C3. Z e raised to minus I Z T over V plus I delta. That's equal to, if I take the limit delta tends to, which is e raised to minus delta T. And in the limit delta tends to 0, this is equal to 1. But I still have to show, if I want to evaluate this, I still have to make sure that this is actually equal to 0. Expectation is that this will be equal to 0. And that will be okay because of this features in here. So let me try to do that here. Minus 1 over 2 pi I. C3 will be, you're going from 0 to minus 5. 0 to minus 5. Let's again substitute z is equal to r e raised to I theta. So this will be I times r e raised to theta. Theta, and again it's the exponential that matters. So it's exponential of I r cosine theta t, and this is minus r sine theta t. Oh, there's a minus. So this is plus. And divided by e raised to I theta plus. So there was a minus I, and then r cos theta minus I. And I, we have this r plus. But this quantity is equal. So for theta less than pi, less than 0, but now this is minus pi, right? So this is maybe I should say the other way. So theta is basically greater than pi and less than 2 pi, which is the same as 0 to pi in the negative sense. So this is equal to negative sign. P is greater than 0. So that goes to 0 as r tends to infinity. So that argument, if you do this limit in the proper sense, then this goes to 0. So put this back, the contour C3 is 0. So theta of T plus 0 is equal to exponential of minus I delta T 1. That's equal to, so or T, which is what we needed. Notice it's more making sure that in that particular type region of the contour, that's the right right contribution you get. So maybe I should if I have 1 more minute, I should give you a quiz. So try to do evaluate dz over z plus IA. So let's say A is real, but then A could be positive or negative. Do this for positive and negative. So first do positive and negative. So that's a simple exercise you can do. I'm not sure if this is part of your homework or not. Maybe it is part of your homework. If it is part of your homework, then you don't have to do this. This is just for practice. It's one of the simple contour integrals where there are all these features that you only need this information where you try to connect one piece of the contour to the other piece of the contour. And yeah, try to do the homework. There are reasonably good examples there. There are lots of examples you can build, but then I have to make it a finite homework. That's too long. so that's- Okay, I'll stop here. Thank you. Hey,
You can suggest.
you.
But
Tomorrow, right? Yeah,
yeah, we meet tomorrow evening.
thanks.
You have a nice day. Bye.
I can try to do this. You always try to do this. Yeah, I can. I can do this. It's fine. I think you should relax. What do you say?